Hello again. Welcome to the second part of today's lecture. We stopped before at the different data rates of Zigbee. Now we're going to move on to LoRa. Now LoRa stands for long range. LoRa follows the standard of the LoRa Alliance, which is a similar standard to the IEEE 802.15.4. However, this specific standard was created by a bunch of companies. They came together and said, okay, let's make a standard for LoRa. So all the upcoming companies entering the IoT sector and want to work with this specific technology, they can abide by these rules. So they created this standard, the LoRa Alliance, and LoRa operations mainly are similar to the 15.4 in lower frequencies, so they don't operate in the 2.4 gigahertz, at least usually, not usually. So they operate more in the 433, 867 megahertz in Europe, and the 902 megahertz in the US. So again, in the ISM bands, but not in the 2.4 gigahertz. Now, as we said, the LoRa follows the LoRa Alliance standard, but since the both the 15.4 and the LoRa Alliance standard operate at the 800 megahertz bands, now does this constitute kind of an interference between different technologies? Of course. If you operate both a Zigbee network and a LoRa network in the same frequency, you will have interference, no doubt. And therefore, it requires kind of network planning to have specific um, minimum distances between the devices in order not to have this kind of in-band interference. Um, Now, let's continue talking about the physical layer of LoRa. Um, LoRa Alliance is a nonprofit association similar to Zigbee. It was first established in 2015. They 15.4 sub-gigahertz is what the LoRa Alliance follow. So again, it's this low power wide area network standard. So if you look at the standard and you kind of see the frequencies that are below gigahertz, you will find the 860 and the 433 bands. Now, the communication ranges of LoRa are quite higher than Zigbee. Now, before we said that Zigbee can go up to 100 meters if you have line of sight communication. With Zigbee, with LoRa, you have communication ranges up to 10 kilometer and even 20 kilometer in suburban areas where you have um, line of sight communications and not so many obstacles in the way of the signal. And mainly the reason for that is because LoRa can work on lower frequencies, and it can actually the devices that use LoRa can actually transmit at higher powers. Now, usually the transmit power can go up to 14 dBm. This is different than Zigbee, that the maximum transmit power was actually 3 dBm. Except for channel G3 for LoRa, it can go up to 27 dBm. And this kind of depends on the frequency of the channel. Another factor that adds to the communication range of LoRa is actually the receiver sensitivity. Now, the minimum allowed received signal strength is negative 134 dBm, and therefore the difference between the maximum transmit power and the receiver sensitivity becomes the link budget, which is 154. So there's an exercise here that I would like to do and to show you guys how this link budget actually describes the communication range. So let's have a look at it. Good. So let me put this in a better format. All right. So here we start with LoRa, right? And then we will do the same thing for Zigbee later on. So let's say that we have a LoRa network. So we're working at the 800 megahertz frequency, right? And we have a minimum allowed received signal strength of negative 134 dBm, and the maximum transmit power is 14 dBm. Now, the gateway configuration so the gateway is this router that we said that collects all the information from the devices. You have an antenna. Usually, an antenna has a certain gain to it, and we can have a antenna with quite a higher gain that goes up to 12 dBi, and you have a cable loss of 1 dB. So at the end, the received power is the transmitted power from the end device plus the antenna gain that you get at the antenna minus the cable loss. And here you have the transmit power is 14 plus the 4.5 gain of the antenna minus 1, which is the cable loss, gives you 17.5 dBm. And this is actually the emitted or the radiated transmit power. So if the gateway is trying to communicate with the end devices, it will transmit at 14, and then the antenna will add this gain, and then there will be losses in the cable. Same way, if the end devices are trying to communicate with the gateway, then they will transmit at 14, and the antenna at the gateway will add the 4.5, and then the cable loss will be loss in the cable connecting the antenna to the processor of the gateway. Good. Now, this minus 134 is the minimum allowed received signal strength. So you will have the 17.5, which is the received signal. It can be degraded by the path loss all the way down to minus 134. So let's take a moment to talk about the path loss. Now, if you stand next to your friend and you speak, you don't have to speak that loud compared to when you stand at the back of the room or at the end of the park and try to speak to the same friend. Now, this is the same way communication works. You have a signal that is being transmitted, and the longer it travels, the more power it loses. And the path loss is the amount of power the signal loses traveling for a specific distance. And here we have a maximum allowed path loss for this frequency and this configuration of 151.5 dB. Now, there are certain models, which means equations that describe the amount of power a signal loses traveling in a certain area. For example, we have the Hatta model for urban areas. So we have here a path loss described by, first, the height of the gateway antenna above ground, the height of the things or the device's antenna above ground. We have the transmit frequency, so the frequency of operation. We have the antenna height, correction factor. We have the distance between the gateway and the device. Now, if we look at this equation here and look at where the frequency is. Now, the frequency here is here, inside the log, right? And before it, there is a plus, which means that the higher the frequency, the higher the path loss becomes. Also the distance, and it also has a plus, which means that the higher the distance, the higher the path loss becomes. So this explains why higher frequencies suffer from larger path losses. Now let's take it for a small city like Oxford. The antenna height correction factor is this way, is described by this way. And for the LoRa network, we know or can estimate the following. Now, the height of the gateway is 30 meter. This is standard. You put it on top of the roof of a certain building. The height of the antenna of a device is 2 meter. It's a kind of an average of a person or a um, um, higher point of sensing a certain value. So if you're measuring heat, for example, you're not going to put it on the floor. You're going to put it on in a corner of the room or on the ceiling. So we take 2 meter as an average, and the frequency of operation is 868 megahertz, which means that this correction factor becomes this, which leads to 1.282. And then you take this value and you substitute in the original equation with the same values that you used here, right? And you get this final equation, which is only a function of the distance because you already substituted all the other variables. And then you flip the equation and you take um, exponential of both sides, and then you get a function of the distance. So you get you get the distance as a function of, or here the distance as a function of the path loss. Then you can substitute with the maximum allowed path loss inside this equation, which is 151.5. And in this case, the maximum allowed path loss describes the maximum allowed distance between the end device and the gateway. So, in end, for urban areas described by the Hatta model, we can get a distance of 5.7438 kilometer operating at this frequency. Good. Now, if we talk about suburban areas, so the countryside, there's a different model. So also the Hatta model, but a different equation that describes the suburban areas. We get a different value. We can substitute and we can get a different equation, which gives us at the end a maximum allowed distance of 10.937 kilometer. So you can see here that the maximum allowed distance actually doubled when we went from urban to suburban. This is a result of having possibly a line of sight communication and also possibly less obstacles in the way of the signal. Okay, so let's move on now to actually Zigbee. Now, let's go in to see for Zigbee operation, we have here a frequency band of 2.4 gigahertz. We have a receiver sensitivity of minus 100 dBm and a maximum transmit power of 3 dBm. These are the stuff that we discussed when we talked about Zigbee before. Now we have a gateway configuration. Now we changed the values as we still followed the same model, right? So we changed these values to kind of accommodate the Zigbee standard. So we have here a nominal antenna of 2 dBi gain. If you have a higher gain antenna, it's still 2 dBi, so nothing changes. You have a cable loss of 0 dB because the coordinator in Zigbee is an actual Zigbee device as well. So it does not have a lot of cable losses. This is not similar in the case of LoRa, where the gateway is a bigger device, consumes more power, and therefore you have more losses. Now, the emitted or radiated power is the transmit power plus the antenna gain minus the cable loss, similar to the last time, and this gives us 5 dBm. And the maximum allowed path loss becomes the receiver, the transmitted power minus the maximum allowed receiver sensitivity, or the minimum receiver sensitivity, or the minimum allowed received signal strength, which gives us 105 dB. Therefore, this path loss can be, again, similar to previously, can be translated to a maximum distance. Now the changes that we see here is the frequency is different, 2.4 gigahertz. Here we have the height of the gateway and the height of the end device are similar because, as we said, they both are Zigbee devices. And here we took 5 meter to describe, for example, an example of a street light network. So you have these devices at the top of the street light, so 5 meters. And again, by substituting in the model, we get a maximum distance of 15 centimeters. Now, what we want to say with this is that if you change a few things, such as the transmit power, so the maximum allowed transmit power, here is 14 dBm, while in the other is 3 dBm. And the minimum receiver sensitivity is minus 134, while in the other one it was minus 100. And of course, the frequency of operation. Although in Zigbee you can still operate at 867 megahertz, and you would actually get a higher distance, higher maximum allowed distance. However, it will never be in the range of a kilometer. So you go from several kilometers that describe kind of a wide area network to centimeters, maybe a few meters, which describes a kind of a personal area network. Okay, so let's go back to our slides and move past the physical layer of LoRa. So as you guys can see here on the right side, you have a description of the different layers of these technologies. So you have, first of all, the modulation that LoRa uses. We're going to talk about that later. In the next slide, you have here the frequency of operation. On top of the frequency of operation, you have the modulation that we'll discuss in the next slide. Then you have the MAC layer that has different classes of operation. Now, as we said, the MAC layer describes the topology and how these devices communicate. So first, when we talk about the topologies, we actually have to say that LoRa um, is mainly a star topology network. And that's because the end nodes must be communicating directly with the gateway. So as an end node, you cannot receive the data sent by other end nodes. This is mainly actually because they kind of separate the uplink and downlink frequencies. So if you're working at the 868 megahertz frequencies, you will have specific channels for uplink, meaning that you're sending data from the end devices to the gateway, and you will have specific channels for downlink, which are the channels where you send data from the gateway to the end nodes. Usually the operation of this data transfer is that the end nodes will use the uplink, and then the gateway will reply with an acknowledge. However, there are 3 different classes for the operation of the devices. The first class is usually the battery-powered devices that are trying to conserve energy. So they usually use the uplink window. So they send information, and then they have 2 downlink windows, which are specified for receiving information from the gateway, either a command or an acknowledge. If they don't receive an acknowledge during these downlink windows, they will shut down, and they will transmit again when they are required to transmit. Then you have class B of devices, which is usually the devices that are latency required, so you need to kind of reduce the latency. And in these devices, the downlink windows are scheduled, which means the devices are synchronized and they know exactly when they should expect data from the gateway, so kind of a command or an update. And otherwise, they use the uplink window whenever they want. So they send an uplink, and then the downlink windows are specified so they can use them when the time comes. Now, class C is the no latency devices. So these devices are ultra low latency devices, and that means that it's very crisp and very reactive. That once the gateway needs to send something, it can send it right away, and the devices will receive it at the same time. Which means that they are receiving all the time unless they are transmitting something. Now, there is a subtle difference between Class B and Class C devices, which means that the devices will upload whenever they want, except that for Class B devices, they cannot upload when the downlink windows are scheduled. The same goes for the gateway. For Class C devices, the gateway cannot communicate with the devices while the uplink is happening. And for Class B devices, the gateway can only communicate with the end devices during the scheduled downlink windows. Which means that if the gateway wants to send something, they might have to wait a little bit until the next scheduled downlink window is opening. And if there is a kind of a full buffer of information, they might even need to wait for 2 or 3 upcoming windows. Okay, so I hope the difference between these different classes is clear. If not, drop me an email, write in the forum, or we can discuss it next time when we have the live session. Good. Now, as we said before, we come back to the modulation. There we are. Now, the modulation in LoRa is quite different than in Zigbee. The modulation is proprietary spread spectrum modulation scheme based on chirp spread spectrum. And a chirp pulse is actually a sweep in frequency on the corresponding bandwidth. Now, let's assume that the distance between these two yellow lines is the bandwidth of the channel, right? And your chirp pulse is a sweep from the low end of the bandwidth to the higher. So the bandwidth is from F low to F high, sorry. The x-axis is the time domain, and the sweep is from F low to F high with time. So kind of the signal goes from low frequency to high frequency. Now let's see a video where actually you guys can hear this up sweep or down sweep in YouTube. Okay.
A plain radio signal carries no information, apart from the fact that the transmitter's been left on. The signal has to be modified in some way to be used to convey information, and there are a number of ways in which this can be done.
So the first part kind of tells us the reason why we actually use modulation, right? Now he will explain more in details how this chirp pulse works. First, how modulation works, and then how chirp pulse works.
Two of the most popular methods are to modify the amplitude and the frequency, and these will be familiar from the fronts of the traditional radio, AM and FM, amplitude and frequency modulation. Listeners to AM radio will be aware that it's more susceptible to interference from natural and man-made sources because it's not as sophisticated as FM, which is clear and resilient, and is a more complex and unnatural waveform. AM and FM will be easily recognised because of their widespread use in broadcasting. Here, we're not concerned with music and speech, but just binary ones and zeros. Digital 1 and 0 signals could be sent using AM by just keying the signal on and off. Crude but effective. With FM, one frequency could be used to represent a 1 and the second for a 0. This is also a common method and called frequency shift keying.
Now you guys can actually hear that when he's just seconds ago, you can hear the different frequencies, right? You have low frequencies and high frequencies, and as the data changes from 0 to 1, also the frequency changes, and this is called frequency shift keying because you shift between different frequencies based on the information that you're transmitting. So 0 corresponds to F low, 1 corresponds to F high. However, with AM modulation techniques, you change the amplitude of the signal. So either you are transmitting or you're not transmitting. And this is similar to kind of knocking. So you have specific durations. During this duration, if you're sending something, this means a 1. And during this specific duration, if you're not sending something, then this is a 0. And at the receiver side, you kind of build these 1s and 0s, and then you get the transmitted signal.
FSK. We can see this signal jumping between its two frequencies here and recorded below in what is called a waterfall display. FSK is important as it's simple to produce and detect and is referred to in LoRa radio transmissions. But LoRa goes further and in doing so becomes more complex and even more resilient to background noise. Rather than just use the two frequencies of FSK, it sweeps between the two like this, up and down. Now, there are two parameters that may be changed on both the rising and falling signals. These are the rate at which the sweep changes, call this the sweep rate, and the range over which the sweep could change, call this the bandwidth.
Now, in the previous curve in the slides, these are interchanged. So they're switched. The bandwidth is on the y-axis and the sweep rate is on the x-axis, just for your information.
There are always compromises in communications, and here there are compromises in both sweep rate and bandwidth. Increasing the bandwidth provides a better quality signal, but bandwidth is at a premium. Everybody is vying for space, and bandwidth is valued and restricted.
Good. So here he explains how when you increase the bandwidth, so you increase the distance between F low and F high, you can actually send more data at a higher data rate, but you cannot easily get bandwidth. So everybody's trying to use the same bandwidth, especially if you're working in the ISM band domain. So you kind of have to find the sweet spot in the middle, right?
Engineering involves maximizing performance using minimal resources. Bandwidths specified for LoRa are therefore restricted under international agreement to 500 kHz, 250 kHz and 125 kHz, and in Europe further restricted to just 250 kHz and 125 kHz.
So in Europe, we have, in the standard of LoRa, the LoRa channels, so the different channels have a specific limited bandwidth of 125 kilohertz or 250 kilohertz. So you can choose only between these two bandwidths, so you cannot actually go bigger than that, right? So this leaves us with the sweep rate. How can we actually get the best out of the sweep rate?
A slow sweep rate is easy to decode and becomes progressively more difficult the faster the change. Here's another potential trade-off. The faster the sweep rate, the more information can be passed, but the more difficult it is to accurately resolve the signal.
So here he explains how the sweep rate is actually affecting the signals, right? So if you're switching between F low and F high, if you're transitioning from F low to F high or from F high to F low at a lower rate, it's very easy to know exactly what is the data that you're transmitting. But if you're transitioning from the two different frequencies at a very fast rate, so the sweep rate is higher, it's very difficult to decode the signal to know the original information. However, you can actually send more information because you're doing it so quickly that you can send more bits per second.
The European system uses 6 different sweep rates, or spreading factors as they're referred to. These are referenced by numbers 7 to 12.
So we have actually in the LoRa standard, similar to the specified channel bandwidths for LoRa, we have specific sweep rates, which are 7, 8, 9, 10, 11, and 12. Each sweep rate combined with a specific channel bandwidth will give us a resulting possible data rate. We'll see that in the slides when we go back.
We've already seen that LoRa devices use a LoRa, which is a protocol where any device can just wake up and...
Okay, so This is now irrelevant for us. Okay, so as we said before, the data rates vary from 250 bit per second at sweep rate of 12 um, and 125 kilohertz to 5.5 kilobit per second at sweep factor of 7 and 125 kilohertz. So here we have different sweep rates, how the sweep rate here being extremely fast, here being moderately fast, and here being very slow. And here we have the different sweeps, right? So this is the unmodulated signal, and this is the signal multiplied by the sweep factor. And the combination of different sweep factors and different channel bandwidth will actually result in a different data rate. So you see here the data rate actually varies from 250 bit per second to 5.5 kilobit per second. However, when you go back to Zigbee and see the possible data rates, we see here you have up to 250 kilobit per second at 2.4 gigahertz, while here you have 5.5 kilobit per second. Now, of course, if you use a higher frequency, so higher bandwidth, like the 250 kilohertz, you will get higher data rates, but you will not get as high as the data rate that Zigbee gets at 2.4 gigahertz. So at the end, it's always a compromise. You need to know your application, you need to know the range of communication, and the amount of data you're about to transmit. And in this way, you can actually design and say, okay, I'm going to use a certain technology or another technology because this is what I need to do, right? So this is the application that I need to design. This is the limitations that I have, and I need to kind of manage that and choose a suitable design. Now, talking about that, we're going to see actual examples of networks that used both different technologies. And here is our first example. So the use case that we're going to present here is smart street lighting. Now, this project is called Mayflower Smart Control. The original application wanted to kind of control traffic lights using Zigbee. So this is the actual brochure of the use case. So we're going to go quickly through it. So the Mayflower Smart Control System is actually an deployed Zigbee solution for streetlights. I don't remember where it was actually deployed, but I remember it actually had like pictures from the field. But the lighting control itself uses Zigbee. So how it works is that it allows street lights to be monitored, switched, and light output to be dynamically controlled. So it actually has these nodes that you deploy on top of the street lights, and just like that, these nodes can control the street lights remotely and even control the light intensity. Now, how it works is that these nodes communicate with each other and with the coordinator using Zigbee communication. The coordinator has a different way of communicating with the outside network using GPRS, which is 2G. And then from the mobile phone network, it can communicate with the internet, goes to the back office where the data can be collected and analyzed, and then the controls engineers can control the lights remotely. Now, here in this document, you guys can see, so here these areas are now have a smart city-like network ready for future IoT applications. The Mayflower supplied and is controlling nearly 320,000 lighting units across 30 different places in the UK and Ireland. So it's actually um, deployed. And as you can see here in this image, is that these different monitoring systems is meshing. So they are the information is in a mesh topology. So the information from here, in order to reach a coordinator here, might not be able to actually go directly. So it might have to jump different nodes in order to reach there, right? Good. Here you have the kind of the specification of the devices. So you can actually let's just look at the um, stuff that we showed you guys in the office document. So you have here, for example, the range is up to 200 meter, which is actually quite interesting for Zigbee networks. So this is a high range of communication, specifically if you are working in the 2.4 gigahertz domain. However, the maximum output power is actually 10 dBm. So this is much higher than the one that we considered in the math example, right? Good. So you guys can look at that here, and kind of if you have questions, just shoot them in my direction. Right. The link is down here. I will also include the PDF document in the Opal folder. Um, so the result of the deployment of this monitoring system has resulted in a saving of 16 million kilowatt hour per year. So this is a huge save in energy, just because you can lower the intensity remotely, for example, at later times of night when there are no people in the street. Good. The second example that we will present is the Things Network. Now, the Things Network is an open platform for LoRa operated devices. It's kind of a cloud, an open cloud, where you guys can control your LoRa solutions, LoRa networks. So let's have a look at it. So you can actually join and have your own dashboard um, uh, for free. So we had a kind of a solution. Uh, I don't remember how to enter it. Yeah. So you have here the overview of the gateway, right? And you can actually, when your nodes, your LoRa nodes are transmitting, you can actually see the traffic. So you can see exactly the time the gateway received the information, the type of modulation used, the rate that is being used in the modulation, the data rate that is being received, everything you can see it here. And I wish I could show you that in real time, but since we're not in the office, I don't have the sensor node, so I can't actually show you that in real time. But um, this would be enough for now. So from here, you can actually take this information, and then you can um, write your own application. Uh, Here. So here you can actually write a specific application that does something with the information that you receive from the nodes, right? So in a way, you can write a specific code that, I don't know, controls the intensity of the light at home depending on the intensity of light outside. And this can be completely automated. Okay. Good. An actual example of using the Things network is Flood Network. Now, Flood Network is an actual network also deployed uh, in real life, and it actually monitors the canals, the different canals in Oxford. So you guys can see the network here in real time. So you have here these dots that tells you um, the different sensors. So here you have a sensor that is measuring water level at Eastwyke Hogacre. You have here a sensor that is measuring at Osnai Lock, another sensor here that is measuring at New Botlai, and it tells you the water level. So the last time this sensor sent data was at 19 hour, which is 6 minutes ago. So I suspect that it sends information every 10 minutes, maybe, possibly. You guys can check it later. Let me know if it's every 10 minutes or even if every hour. Um, you can never actually know. I guess the green ones are the ones that are updated, right? And the blue ones are the ones that are that have no data. Good. So there are many projects that are actually implemented on the Things Network. You can go on the website of the Things Network and see for yourself these different projects and kind of explore the world of IoT. This is the end of our lecture for today. Thank you for your attention. It was kind of a long one. I hope you guys enjoyed it. And if you have questions, send them to me, and we will discuss them next week in our live session. So before the live session, I will upload the second lecture of the Mac protocols. And in the live session, we'll first have a small part of the lecture in live, and then we'll discuss different questions that you guys have. All right, so have a nice day, evening, depending on when you're seeing this. And please give me feedback on the mic. So this is the new mic. I hope it was much better. Good. Bye.